Okay, we've been discussing the simplex method in matrix form for the last 2 hours or so, and you were patient to go through that. Some of you missed that particular lecture. Nevertheless, you have a chance to review it once it's broadcast on the net. I'm going to continue to work on the same stuff, except that we'll concentrate on the simplex tableaus relative to a given basis B. So let's assume we have the problem in the form minimize Cx subject to Ax equals B, x greater than or equal to 0. And we assume, given a basis B, the rank of A matrix is the row rank. It's M. So all the other information that I gave you earlier continue to hold. And so B is an M by M matrix consisting of some M linearly independent columns of the A matrix. Okay? And we assume it's feasible, meaning that the basic feasible solution induced by it is non-negative. Okay? All right, so given a feasible basis B, the partitioned form of the problem was minimization of C sub bxb plus cnxn, basic part plus the non-basic part, subject to bxb plus nxn equals b, xb, xn greater than or equal to 0. That was the partitioned version of the standard form problem. And I also gave you row 0 form, which is simply the same problem where the minimization is on the additional variable z, whose definition is here. Nothing new so far. This, you've got that already. And you've got row 0 here, and you've got rows 1 through m for the second part without the non-negativity. The non-negativity is dealt with on the side without doing anything explicit about it, except that when you identify the exiting variable, you pay attention to it. All right. Now, what we did was we pre-multiplied the second part by B inverse. So first you set xn equal to 0. Then pre-multiply the whole, to get the new current solution, which gives you xb equals B inverse B, which we called B bar. Okay, that was the current solution, which I marked with a bar with objective value z bar defined by CB xb, which is CB times B bar. Okay? All right, that's the current solution. For any xb, for any xn, we have from bxb plus nxn equals b, xb plus b inverse times n xn equals b bar. That's what the equations give you, except row 0. Okay? And which, of course, upon transferring this to the right side, will give you simply the dictionary form that looks in this particular format. Okay? All right. Substituting this in the objective function in row 0, we get, what do we get? We get z equals the current value z bar minus CB B inverse n minus Cn times Xn. I'm skipping certain steps here, but we've gone through this. All you're doing is you take xb equals b bar minus b inverse n xn, put it back in place of xb here in row 0, and then once you put that back, xb of course disappears. In place of it, you have an xn with a certain multiplier here, okay? And then you simplify the equation by collecting everything that multiplies xn in a parenthesis, and that parenthesis is what you see here, okay? All right. And I gave a name to this. This was R sub n. So, and the equations with these manipulations show up in the following form. Z minus a vector of zeros times xb, I'm using this, plus what we called Rn. The plus, of course, this negative becomes plus here on this, times xn is equal to z bar. That's your first row 0. And then the second part, what is the second part? It's this part with xn transferred to the right side. So identity times xb plus b inverse times n xn equals b bar. You're still minimizing z here, subject to this way of, subject to these constraints, which are equivalent to the original constraints because you just pre-multiplied by a non-singular matrix, B inverse, and then you substitute it in the top with xb, xn greater than or equal to 0. That's your row 0. And the remaining part gives you row 1 through row m. Okay? And your simplex tableau precisely matches this boxed portion of the system with all the variables removed. That's it. So your simplex tableau corresponding to basis B is the following tableau. In partitioned form. You have all your variables associated with the columns. The first column is always reserved for z. The basic variables are listed on the side, z and the components of xb here. Okay? And then you simply copy down the coefficients. Z has a coefficient of 1 here, coefficients of 0 elsewhere. So that's why you have the unit vector with the 1 in the first position. xb has 0, a row vector of zeros in row 0. See, you don't have xb here, which means it's 0 times xb. Okay? Plus, you've got identity for the rest of the rows. Rn has, Xn has Rn, and you've got B inverse n here for that one. The right-hand side column is the current value of the objective function z bar and the vector of current values for the basic variables, b bar. That's it. So this is what your simplex tableau houses. That's the basic information. Now, let me just define a few other things here. Let's define R sub b similar to R sub n. How do we do it? We take again the vector cb, multiply it by cb by b inverse, and then instead of using n, we use the basic columns b, and then we subtract the basic costs cb. So this is the matching definition for the basic part, the vector of reduced costs for the basic variables. And of course, this is equal to 0, because b inverse b just is, that's identity, then that gives cb minus cb, which is equal to 0. Okay? That's why you have that. That's your RB, actually. Okay? And let's also define the vector yj in the form b inverse aj for every variable. Assuming that there are n variables, you have a definition for each variable j. Yj is b inverse times the original vector, original column aj of the A matrix. Now with this, the tableau in non-partitioned form looks like this then. If I don't separate out the basic and the non-basic part in the columns, they are whatever they are. The columns that go into B are the basic columns. The columns that are out of the B are non-basic columns. So in that case, you still have your 1 and 0 here. We're still talking about the same basis, B. Okay? What you see here is RB and RN, which is your reduced cost R in non-partitioned form. So here R is simply RB and Rn in partitioned form, but without the partitioning, it's equal to, what is it equal to? CBB inverse times the A matrix. So rather than the B or the N, you just take them all collectively. Okay? CBB inverse times A minus the cost vector. That's your R. Okay? So if you want to write that down, well, whatever. It's just here. Okay? CBB inverse A minus C. In the lower part, you have B in partition form. You have B inverse times B, and then B inverse times N, which is nothing but B inverse times A without the partitioning. Okay? And the right sides, of course, don't change. You've got the same information. This is useful to remember. Okay? Everything is pre-multiplied by B inverse in the actual constraints, and the top is cleaned up to replace the original cost by the reduced costs. All right. Other than that, there's really nothing that I want to mention here. So let's just conclude that part. Okay. And let me just go on with other stuff. Let's continue our discussion with alternative optima. Suppose B is an optimal basis, which means that when you look at the tableau, your tableau has this information. Okay, it has this information. The top has the reduced cost. Since by assumption B is an optimal basis, the reduced cost must be in a certain way. What should they be? They are all, this is a minimization problem. You are able to enter something for a minimization if there's a positive reduced cost. So they should all be less than or equal to 0 in order for this to be optimal. Okay? Due to optimality of B. There's nothing to enter here. That's the vector form. This is simply R. Okay? Now, if you look at the jth reduced cost, one at a time, then Rj is simply the same definition, CBB inverse Aj. So you just pick the jth column of A minus the associated cost Cj. Okay? That's your reduced cost for the jth one. Now, this is equal to 0 for all basic variables. Why? Because of the way we defined here. Where was it? See, RB is always 0. Okay? They're always 0. So obviously, the basic reduced costs are always 0 by definition. Okay? So this inequality is always satisfied by them. RB equals 0, always satisfy the inequalities. For non-basic J, what you have here is this one, and they are less than or equal to 0 by assumption on the optimality of B. Okay? And these are for the non-basic variables. Now, whenever this is strict inequality, entering that particular variable would tell you that the change in z relative to a non-basic variable xj would be how much? The negative of the reduced cost. You remember that, right? Because, we've gone through that a number of times actually. Now, if Rj is negative, of course, then minus Rj will be positive, in which case entering that particular variable would actually increase the value of z because, this is a positive rate of change, which means, of course, this is something you would like to avoid because you're minimizing, okay? You don't want the objective value to go up. That's why you impose this or you have this condition. Now, however, if it is the case that if Rj equals 0 for some j in the non-basic part, then the rate of change is 0. Then z is defined by the current value minus Rn xn, which is equal to z bar minus the summation. That's just the dot product of the reduced costs with the variables for non-basic indices. And if you keep, let's change that to, let's make this a particular index. So let's just change it to, for example, k. Okay? Because I'm using the j here. Okay? So in this case, if you keep all of the xj's equal to 0, except x sub k, okay? So if I keep my non-basic variables equal to 0, or if I keep them as non-basic other than the kth one, in that case, this summation will have only one non-zero term because xj's will be 0. It will be rk zk. But rk by assumption is equal to 0, which means that you're not changing the objective value. It's still the same. Okay? Hence, we can enter xk whenever, of course, rk is equal to 0 in the optimal tableau and obtain a new basic feasible solution where xk becomes basic now, somebody else becomes non-basic. Who is that somebody else? Well, you look at the minimum ratio again and find a minimum ratio, and that tells you which basic variable becomes non-basic, okay? So this leads to a new basic feasible solution that has the same objective value z bar. Of course, since these are alternative optimal solutions, they must have the same objective value. Okay? The leaving variable is found in the same way. By how? You simply write xb as a function of the entering variable, so it will be the current values minus the vector y sub k, which is the b inverse ak. Remember that. I gave you a definition for that. Okay? So that y sub k is b inverse ak times the variable xk, which is the entering variable, whose reduced cost is 0. And, of course, this tells you that xbi is equal to bi bar minus yik times xk for I going from 1 to m, as usual. Whenever yik is 0 or negative, this particular, the new value of xbi will only be either bi bar or will be something more than that. Okay, bi bar is already non-negative, so the ratios for imposing non-negativity is required only for yik that are positive. Okay? So you choose the minimum ratio b r bar divided by yrk, which is picked as the minimum of the bi bar values divided by yips over all those I, such that yip is, sorry, not p, k, this is k. Yik values are positive, okay? Of those indices I, for which yik is positive, you have the minimum ratio. So it's the same old stuff. There's nothing new. Let me give you an example for this. This is an example for alternative optimum. So suppose you're minimizing, well, let's take this as minimization of z minus 2x1 minus 4x2 subject to x1 plus x2 plus x3 equals 5. x3 is a slack variable. The actual constraints are less or equal to form, but I'm just adding my slacks here. Okay, x1 plus x2. Sorry, this one is x1 plus 2x2. I made a mistake. Plus x3 equals 5. And the second one is x1 plus x2 plus the slack variable x4 equals 4. So this is the standard form of the problem. So we'll just go through the iterations. Initial basis. What is the initial basis? You just pick the columns of the variables x3 and x4 as your basis matrix because it gives you the identity, which is easy to work with. Initial basis B is 1, 0, 0, 1, where the columns are associated with x3 and x4. Okay, that's your initial basis. So B inverse is the same. And for that reason, the constraints look exactly in the same way that they show up in the standard form. Your basic variables are x3, x4, and you've got 1, 0, 0, and then you've got 2, 4, 0, 0, 0. That's the row 0 equation if you just take the xj's to the left side of that equation. These are your basic variables. And you've got 1, 1, 2, 1, and 1, 0, 0, 1, and 5, 4. So in this case, your B bar is 5, 4, because you are working with identity at the beginning. B bar is the same as your B, okay? All right, so that's your initial tableau. Which is just the row 0 form of this equations. So I simply took my row 0 and took my rows 1 and 2 and copied down the coefficients. That's it. Okay? For those of you who may have a little bit difficulty absorbing the details. All right. At this point, we have an entering variable. I can enter x2. This is a minimization problem. You choose the most positive reduced cost because the rate of change in z, when you allow x2 to become positive, is minus 4. Okay? For each unit increase in xt, you go down by 4 units in the value of z. What is the current value of z? It's 0. Okay? All right, so then you look at your minimum ratios, 5 to 1, 4 to 1. So 5 to 2. So this one goes out. And then you want to create a unit vector here in the entering column. And so you pivot on that, on the circled element. What do you get? First of all, x3 is replaced by x2, so that's your x2, x4. And you pivot. When you pivot, you divide the row 1 by 2, so that gives you these numbers. Okay. And then to create a 0 in place of 4, for example, what do? You multiply 1 by -4, the negative of what you see here, and then add it to the top row, which will give you, so it will give you minus, this one is 1, 0, 0, it doesn't change. This will be minus 4 times, minus 4 times 0.5, which is minus 2 plus 2. That one also becomes 0. It's just coincidentally. This one is definitely 0. This one, it will be minus 2 plus 0, so minus 2. This one is 0. This one is what? Minus 10, right? You went down because you're minimizing. Anyway, you compute the same things. Anybody has it? Yes. What is it? How much? 1/2. 0. Minus 1/2. 1. $1.5. Let me just check. Yeah. Yeah, this seems to be correct. All right. At this point, the basic variables are x2 and x4. So these are basic. And for that reason, of course, you have your 0 and 0 in row 0. But then you have another 0 here, which is a non-basic one. So you can enter that and generate a new basic feasible solution. But before I do that, what is the basis here? What is the B matrix associated with this? It's the columns associated with x2, x4 in the same order as they are listed here. Okay? X2 column is from the original, is 2, 1. X4 column is 1, 0, 1. So that's your basis here. Of course, you don't see it here because everything is, in this tableau, everything is pre-multiplied by B inverse. It's disguised for that reason. So this part of the tableau is B inverse times the original matrix A, which tells you that 2, 1, 0, 1 inverse multiplying whatever you've got. 1, 1, 2, 1, 1, 0, 0, 1. And the output of this multiplication should match what you have in the tableau. Okay? All right. So, at any rate, at this point, I can enter this without changing the objective function value, without making it go up. Okay? And we still look at the minimum ratio, so this should be the minimum ratio. And you pivot on that, you get a new basic feasible solution, a new extreme point. So when you do that, what do we get? I've got that. Okay. And the basis corresponding to this one is, of course, the columns associated with x2 and x1. x2 column is 2, 1. x1 column is 1, 1. And the information in the tableau is, again, B inverse times the entire original A matrix. Okay? And of course, the top values, the row 0 numbers, are simply your reduced costs as they are defined in our notation. Okay, so this is also optimal. This is optimal. This one is also optimal. Are they the same solutions? No, they are not. Okay. The point here is x1 is non-basic and 0, x2 is 2.5, x3 is 0 because it's non-basic, x4 is 1.5. That's your extreme point in four-dimensional space. In this case, let's just call that x bar. In this case, you have a new solution, x cap, which is the following. x1 cap is how much? 3. x2 cap is 1. The other ones are non-basic and 0. The objective value is 10 here, minus 10. And it's also minus 10 in this one. Of course, because they are alternative optimum solutions. And if you're interested in the set of all optima, well, can you generate a new basic feasible solution which is different from both of them and still optimal? No, basic feasible solution.
No. You can just change
x4. Well, the only one you can enter here is x4, but then if you enter x4, you get back to the old solution. Okay, so there's nothing new. There are two different basic feasible solutions that are both optimal. So the set of all optima is the set of all convex combinations of the distinct extreme point optimal solutions. In this case, you've got two of them. So you multiply one of them by lambda, the other one by 1 minus lambda, and then you get your optimal solutions as dependent on lambda. So the first one is 0, 2.5, 0, 1.5. This one is 3, 1, 0, 0. And so you got 0, 3 minus lambda here, 3 minus 3 lambda. You've got 2.5 lambda minus lambda, that's 1.5 lambda. So 1 minus 1.5 lambda. Did I do it right? 2.5 and minus 1, yeah, 1.5. No, plus, this is plus. I knew I made a mistake, yeah. The third one is 0, 0, so it's 0. This one is 1.5 lambda. Right? Okay. So any number lambda between 0 and 1 will give you a distinct solution. Whenever lambda is equal to 0 or 1, you get a basic feasible solution which is optimal. Whenever lambda is strictly between 0 and 1, you get an optimal solution which is not basic. Okay? Nevertheless, they are optimal. Another thing that you need to worry about is the case of having an unbounded solution. The optimal cost is minus infinity if it's a minimization, or plus infinity if it's a maximization. So how do you recognize this? In the following way. So let's assume we have a feasible basis B on hand. And let's look at the simplex tableau. I don't think I'm going to need xj, so let's just look at this one. Okay. Okay, the right-hand side columns are simply the current values of the basic variables obtained by B inverse B. Okay. Z bar is CB B inverse B. And the first column is nothing unusual. It's the same old unit vector. For x1, you have the reduced cost R1. For xk, you have the reduced cost Rk, Rn. So you've got all your reduced costs like that. What do you have here? Over here, you have B inverse times the original A1 column, which is the y1 vector. So remember, I defined yj to be B inverse aj, and it has all these numbers, y1j, yij, up to ymj. So we're just using this information. This is y11, yi1, ym1. For the kth one, we have y1k, yik, ymk. Similarly, for the last one, y1n, yin, ymn. Like that, okay? This part, the y part, is B inverse A. That's it. Okay. Assume there's a non-basic variable xk. So I'm assuming xk is non-basic. Okay? Such that the reduced cost Rk is, this is a minimization problem, so consistently defined by a feasible basis for a minimization problem. Let's add that. Okay? So, assume there's a non-basic variable xk which prices out favorably, meaning that the reduced cost is good for you. So, positive, yes. It's positive. So, it will make you go down, okay? but with a y column, yk column, which is less than or equal to 0 in each component. Now, the one I happen to pick does not have to have the most positive RK here. I'm not requiring that. There is a positive RK for which the column underneath is all non-positive, less than or equal to 0. Then, of course, when this is the case, there's no ratio to test for. In other words, there's then no blocking occurs. Currently, xk is 0 because it's non-basic, and I want to increase it as much as I can until some blocking occurs. But blocking can occur only if yk has a positive entry in it. The blocking will occur at the minimum ratio, but there's no ratio here. Whenever the yik's are less than or equal to 0, then the xpi's will only either stay the same at their current values or will increase. Okay? Hence, xk can be increased indefinitely to make z, or to make the optimal cost minus infinity. Okay? Does everybody see what's going on? If you have a question, ask me now, because I'm assuming that you've mastered, or you're keeping in your head what we discussed earlier. Okay? Without that, of course, if you're sort of disconnected from the previous stuff, you lose the connection. Okay? What is the connection? Again, for those of you who may have difficulty, this is a summary statement for the following. We are having xpi, the ith variable. Xk will be made equal to some number, okay? So the ith variable is my ik times xk. This is true for I going from 1 to m. This was the equation we looked at. And when xk is allowed to become positive, if this guy is 0, xpi is not changing. If this guy is less than 0, it will be adding something to bi bar, so there's no blocking. Okay, that's what I was referring to here. Okay, all right. I'll give you an example in the after the break. So let's take a 10-minute break.